Okay, let's get started. It's my pleasure to welcome our very own Professor Linda Hsieh to the colloquium stage today. Linda got her PhD from MIT, working in a group of Professor Joe Czajkowski, where she made really pioneering contributions in both the synthesis and characterization of a family of quantum materials known as kagome metals. These are special materials in the sense that they exhibit both strong correlation effects and non-trivial topological effects in the same material. And over the past few years, it's really become a very intensely studied field in condensed matter. After MIT, Linda was awarded a Chodorow Fellowship from Stanford, where she conducted postdoctoral research in a group of Professor Ian Fisher. And there she made quite a pivot from her graduate studies, where she used some high sensitivity strain-based thermodynamic measurements to study what are known as heavy fermion materials. And she used this technique to uncover some very interesting exotic order parameters in some of these materials. Linda started her faculty appointment at Caltech in September 2023. Her lab is, getting close to 100% completion. And just this past summer, she was awarded the prestigious Moore Fellowship in Material Synthesis. So we're very excited to hear from Linda today.
Thank you, Dave, for the kind introduction. So can you guys in the back hear me? Okay. Okay, thanks, Nick. It is my great pleasure to be here, to be giving you a flavor of the kind of research we do. And as Dave just mentioned, that we started as a group at Caltech about a year ago. And today I will tell you a story before I came here. And at the end, if time allows, I want to show you some snapshots of the ongoing research projects we're pursuing right now. And at least I think they are quite interesting and may take us somewhere new. Great. So in case you're wondering what the pictures I'm showing you on the left are, they are motifs of the Japanese style door window panels. And this particular motif on the lower left is what Dave briefly mentioned. It's a kagome structural motif. And as I will try to convince you, it's also a very nice lattice platform to study the physics of frustration. Okay, so before I go to the science, in order to better introduce our group to you, I find it really important to show you the kind of experiments we are setting up to do at Caltech. And apologies if this slide is too busy. So as we are experimental condensed matter physicists, as you can already see from this slide, there are two very important components of our lab. So the first part is about material synthesis, and here are a few pictures of single crystals we are able to grow in our lab that's located one building away. So these are you can see that this regular shape of these single crystalline materials is actually a direct reflection of the underlying symmetry of the atomic arrangement of at a macroscopic scale. And just to give you a sense that these grids are on the order of 1 millimeter. So, for instance, this hexagonal crystal is implying that at a macroscopic scale, the atoms are forming a hexagonal arrangement. So with this capability, we're able to explore a very wide range of phase space that comes from the product of the periodic table and the ways the different atoms can arrange them into two-dimensional or three-dimensional crystalline structures. Right. So more importantly, with this capability, we'll be able to pursue a particular physics question relatively flexibly when one comes up. And I'll show you some examples of such questions. So the second component of our lab, which is sort of what sets us apart as physicists as opposed to synthetic chemists. So this is a panorama I tried to take in our low temperature measurement lab that's newly renovated in Linghall again. And here you can see a few cross stats here, and one of them is actually installed across the floor. And there are a few different racks with locking amplifiers and other types of electronics. And with all this, we are able to measure the material properties at low temperature and high magnetic field. And this would give us information about the transport and thermodynamic properties of the material. And we can then infer about the underlying physics of the electrons in those systems. So if you're interested in any aspects of the lab, just let me know. I'd be happy to give you a lab tour and talk more about the experiments themselves. Okay, so without further ado, you might recall from the very beginning that we were going to talk about frustration. And those are two pictures that pops up if you type frustration in Google image search. And this is something we all experience at some point. But today I'm not going to focus on frustration as an emotional state, but rather as a physical phenomenon that would serve to be a driving force for new physics. So let me try to define what frustration in physics means. It refers to the impossibility of simultaneously satisfying all possible constraints of a given Hamiltonian. So the term frustration was first coined around the 1950s. So the choice of wording itself is not completely positive, right? But I think it does have a point that it does capture the dilemma the system is facing when you're trying to minimize all the energy terms in the Hamiltonian, while the different terms are putting conflicting constraints to the system. Okay, and you can imagine that this would be especially important for condensed matter systems, as the macroscopic number of the constituents would really amplify the effect of these competing terms in the Hamiltonian. So here I want to give you some examples of the consequence of frustration. So the first example is about the space packing problem. And so here, if we look at this system, if we imagine how we live in a two-dimensional world and our atoms, for some reason, would like to form this pentagon to save energy, right? And also, in order to save energy, we would also like to pack as many atoms as possible in the two-dimensional space. And if you try to pack those pentagons in the 2D space, there is a problem. Where you can see that if you try to pack them, you always see some missing angles here, where you can't fit another pentagon into the space. So there are a few ways of going around this. Number one is to try to buckle into a higher dimensional structure, and for instance, if you get this three-dimensional dodecahedron structure that would have this pentagon arrangement at each of the surfaces, and would sort of mitigate this problem. And the other way of going forward is to stick in the two-dimensional space. But here you would result in a rather complex structure, which is quasi-periodic, meaning that you cannot define a simple unit cell that is translated across the entire space. So as you can already see from this example, that frustration is a sort of a driving force for complexity in structure. So this problem is relatively classical and looks purely geometric. And in the following, I want to show you an example where the frustration concerns electrons, which are quantum mechanical objects. So this is another context that frustration is often discussed about, where we can imagine that we have three different localized electrons that's on this triangular motif, and they are subject to this antiferromagnetic interaction. And you can already see from the sketch here that the antiferromagnetic interaction wouldn't be simultaneously satisfied for the three bonds, right? And as a quantum mechanical language, this antiferromagnetic interaction would favor the formation of singlets, and this means that on this triangle, not the three electrons cannot be simultaneously be in one singlet state. So this would lead to a massive. This can lead to massively degenerate ground states for different arrangement of the antiferromagnetic spins, and if the interactions are quantum mechanical on this so-called kagome lattice, we'll be able to realize the ground states that would be a superposition of these massively degenerate quantum mechanical states. And this is closely related to the ability to generate long-range quantum entanglement in this so-called spin-liquid phase. And this is also an idea that's intimately related to Phil Anderson's idea of resonant valence bond idea for the high temperature superconducting phases. So the take-home message for this part is that the frustration can be quite a unifying thing in different aspects of physics, and it is a driving force for complexity and also emergent ground states and other physical phenomena that wouldn't be possible if every term is happy in the Hamiltonian. So this is sort of the outline of today's talk. So in the first part of the story, I would like to focus on the frustration of hopping of electrons on the lattice through this object called flat bands. And this part is organized as follows, where we'd like to first spend some time talk about how we get this frustrated hopping from a model perspective, and then we'll try to connect them to real materials. And at last, I want to show you what we find experimentally, which may or may not be expected from the first place. Right, so this is one of the, in my opinion, pretty exciting point of experimental physics, especially with condensed matter, where you cannot always precisely predict what you would be observing finally in the experiment as for the material as a whole. And at the very end, I would like to show you some ongoing examples of ongoing projects, also along the lines of trying to utilize frustration to give rise to some unconventional physical responses. Great. Okay, so how does the frustration in hopping work? So first of all, I want to just remind you what does unfrustrated hopping look like. So if you were taking physics 135, taught by either Gil or me in recent years, this should look familiar to you, right? This is the hopping Hamiltonian on a lattice, and this is an example of an unfrustrated lattice in terms of hopping. And if we solve this hopping Hamiltonian, the eigenstate of the system would be this dispersive band, and the eigenstates are spatially extended block waves. and each of the different states would be labeled by their crystal momentum, and it sort of characterizes how rapid these wave function would vary in space. Right. And the kinetic energy of those electrons is characterized by the bandwidth, which is both proportional to the hopping integral itself, as well as the number of neighbors each electron would be able to hop to. So there can be a scenario where such hopping would become frustrated. So I'll give you a few examples of how this would come about, but here let's just focus on the results here. So if the hopping gets really severely frustrated, right, we are able to get a so-called flat band where the energy versus momentum dispersion would have no width. Would have no width, and here you can see that what we essentially get is a macroscopic number of degenerate states here. So here in this plot, we still label the states by momentum, but as you might recall from quantum mechanics, right, if we take linear superpositions of the eigenstates, we still get within a degenerate manifold, we still are able to get the eigenstates of the Hamiltonian. So therefore, very peculiar feature of the flat bands is that it would allow both k-space and real space eigen wave functions, and this can be connected with each other through a Fourier transform. So this might seem a very esoteric point at this stage, but as you'll see, that we'll discuss a lot about the mechanisms of stabilizing such flat bands from the real space eigenwave function of the flat band itself. Great. So the second remark I want to make here is that now we have a very degenerate quantum mechanical manifold. Therefore, any interaction we would add to this group of states won't be a perturbation. Right? So therefore, this is a really nice platform to look for symmetry breaking or other correlated states. So the last comment I want to make here is that sort of a trivial way of making a band looking flat like this is to simply turn off the hopping by forcing t to be 0. And I'd like to just clarify that the flat bands we're interested in is different from this trivial case, and it will really come from the frustration of the different terms in the hopping Hamiltonian. So these are a few very general remarks about flat bands, and in the following, let's take a look at how we can, from a model perspective, create such flat bands. So in lattice models, because lattices are what electrons are living in for the kinetic matter materials. Okay, so as a matter of fact, finding a flat band on the lattice was a sort of old theoretical problem, and this is one of the first theoretical models of identifying the flat band on a lattice model from Beal Sutherland about 40 years ago. So here is the original illustration of the lattice. In case this is too overwhelming, you can look at the magnified view with a smaller number of atoms here. So you can see that part of this lattice would resemble the diagonal projection of the rolling dice, and therefore this is called the dice lattice. And you can imagine physically implementing this lattice by putting the different atoms colored differently here at different heights to realize this hopping network. So if we solve this nearest neighbor hopping Hamiltonian with all the different bonds taking the same hopping strings, we'll be able to get this spectrum here. where you can see that there's a very peculiar feature at zero energy that has no dispersion across the entire two-dimensional Brillouin zone for the lattice itself. So it's very easy to mistake this as the zero line of the plot, but please trust me, this is indeed a set of degenerate quantum mechanical states at zero energy. So now we can take a look at what is the origin of the flat band by looking at its real space eigenwave function, because as you recall, we do have real space eigenwave functions for the flat band. So here is an illustration of the flat band on the dice lattice that's taken from the more modern literature, where you can see the minimum real space eigenwave function is located on these 6 sites, and the odd numbers would take a negative sign of their wave function, and all the even numbers would take a positive sign. So there is an alternating sign pattern across this loop. Right? So starting from this wave function, we can actually figure out that any attempts to hop out from this region from the wave function would be exactly cancels out by the destructive interference from the hopping strands from the neighbor atoms. So therefore, this is really eigenstate of the hopping Hamiltonian, and also it's a completely localized state in this case, right? And the mechanism of the localization really comes from the frustration of the hopping on the lattice itself. So there's one comment I want to make here is that what's key for realizing such a real space eigenwave function is really coming from the connectivity of the lattice itself. So I'd be happy to show you the exact condition for a given lattice to realize such a flat band wave function from the graph theory afterwards, if you're interested. So here I would just give you a simple counterexample where this kind of loop state won't be the eigenstate of the Hamiltonian. So for instance, if we have this triangular lattice instead, which we know is an unfrustrated lattice in terms of hopping. Right? So if we can still artificially construct this 6-side loop state, but you can see that the localization of this state won't be complete, and there are many channels for this particular wave function to leak out, and this is not an eigenstate of the original Hamiltonian. And so we won't find a flat band as shown here for this triangular lattice here. Great. So over the years, there is a growing number of lattice models that are found to host such sign alternating flat band wave functions. And here I'm showing you a few representative examples along with the time that they were first discussed. So here you can see that this sign alternating pattern of the real space eigenwave wave function are more or less realized for most of them. And the first row of these models are crystalline lattices. And aside from the dice lattice, there are leaf lattice and decorated square lattice, which are closely related to each other. And there's also this kagome lattice, where you can draw the lattice point by putting an atom in the middle of this hexagonal network. So aside from crystalline lattices, there are quasi-crystalline and also hyperbolic lattice models that can support such flat bands. And the hyperbolic lattice itself can be quite challenging to realize in solid-state systems, but we can imagine, building artificial lattices from for instance, superconducting circuits to really access the flat band physics there. So for for us as a condensed matter experimentalist, we would like to focus on the crystalline lattices, and in particular, we want to focus on the kagome lattice, as it does look a little bit less artificial, and then some of its other cousins here. Okay, so before I go ahead and show you the actual materials that can help us study the flat bands on these lattices, I want to take a step back and just show you the flat bands in a variety of condensed matter systems. And one of our ambitious goals is that perhaps we can use the lattice to provide alternative routes to realize such flat bands, such degenerate electronic manifolds, besides the much better studied lambda levels in two-dimensional electron gas, as well as the recent frontier of using Morey and van der Waals superlattices to realize flat electron states. And here you can, in both of these cases, you can see these really flat degenerate flat bands across the two-dimensional gradient. So both of those cases are living in two-dimensional electrons. And already there's a lot of different symmetry breaking and fractionalized phases that's realized and driven by these flat electronic bands. And one of the difference we can potentially make is that if we can realize the flat band that's driven by the lattice itself, we'll have a length scale that's on the order of angstroms instead of nanometers, which is the case for both of the cases that's shown here. And also we will be able to engineer the materials with different elements on the periodic table to sort of tune the strength of correlation that we have in the system. Okay. So now we want to go back to the lattice models and try to focus on the kagome lattice. So if we try to look at the lattice itself more carefully, right, it's going to be a hexagonal network of corner shared triangles. And you've seen this lattice very briefly at the very beginning as a platform to support this frustration of anti-ferromagnetic interaction. So here, it's also found to be able to support the flat band states where here I'm showing you two different real space eigen wave function of the flat band states. So for the minimum real space eigen wave function, you do again have this 6-side states with alternating sign patterns. And this larger loop here is actually a linear superposition of this smaller loop that's located on 3 adjacent sites. And for all those flat band with real space wave functions, right? So this frustrated hopping is always at play when this localized wave function that is interfacing is trying to hop out from the region where it is known. Okay. Okay, so in order to realize these flat band models in real materials, what we should be starting with is our systems where this hopping Hamiltonian would be valid in the first place. So this would lead us to focus on metallic materials that would structurally contain this kagome lattice. Okay. So now I'd like to get to the nitty-gritty of trying to realize this lattice in real materials. So one question you might have by looking at this lattice itself is that there seems to be a huge void in the middle of these hexagons, right? So how it doesn't look like energetically stable. So how are we able to stabilize this kagome lattice itself? So the way of going around this is to put a second element into the middle of the large void space. And the second element needs to be electronically different enough from the first element that's forming the kagome lattice itself, so that we can treat their electronic states separately. So here you can see an example of such a kagome structure that's composed of transition elements that's forming the kagome lattice itself, while the tin, which is a p group element, and is very different from iron as taking the void space. So with this as the building block, together with another motif that's the honeycomb structure of the second element. This is the binary compound we could identify that would host their this kagome lattice in their crystalline structure. And here I'm only showing you the compounds between iron and tin, but you can easily imagine replacing iron with other transition elements and tin with other p group elements without really impacting the stability of the structures. So if we try to stack those kagome layers right on top of each other, I will get this AB stacking, meaning that the kagome layers are shipped on the two layers are shifted in the AB plane from each other. And if we stack them across this spacer layer, we are able to get the AA stacking, meaning that the kagome layers are just vertically displaced from each other. Right. So the middle material actually realizes the mixed stacking between the two kinds, and overall it has ABC stacking forming a robohedral structure. Okay. So aside from these binary compounds, if we add the third element into the structure, we get a lot of structural flexibility. And here are three examples of ternary kagome compounds, where you can have these little sulfur atoms or bigger rare earth and much larger alkali metals in between the kagome structures. But nevertheless, the common structural motif across the entire class of material are these two-dimensional kagome layers within the AB plane that's highlighted by red here. So the reason I wanted to show you here, show you all these new varieties here, is to show you that now this is really a large family of materials that are actively investigated in the field. And this is partially thanks to the band structure of the kagome lattice itself. Aside from the flat band I was focusing on today, right? There are also a lot of other interesting features here, which include direct fermion states near the K point here. And this is very analogous to the direct fermions in graphene, for instance. And there are also other singularities in the material. For instance, near the endpoint, there is a saddle point of band dispersion, and this would induce also a peak in the density of state and can serve as a driving force for instabilities for those kagome bands. And there's a lot of discoveries in the field that are from each of these peculiar band features. And for today, in order to focus on the flat bands, we're going to stick with the binary kagome compounds. Also for simplicity of the chemistry of it. Okay, so now we can start to take a look at our experimental results. So first of all, I want to show you the photoemission spectroscopy on two isostructure compounds, iron tin and cobalt tin. So if you're not familiar with photoemission spectroscopy, you can just think about it as the experimental measurement of the band dispersion below the Fermi level, right? And those are a few different crystals I've grown when I was in my PhD, and I think you can see from this is a transmission electron microscopy cross section of the iron tin crystals, and you can already see from here that there are two different layers in the structure, and these more densely packed atoms are the corresponding to the kagome layer, and the larger atoms are corresponding to the spacer layer of the T here. Okay. So if we go back to the photon emission spectroscopy of both of these materials, you can see as a function of the momentum and along the energy axis, right? In both of these cases, you can see flat electronic states across the entire two-dimensional brilliant zone. And coincidentally, both of them actually would locate around minus 200 millielectron volts below the Fermi level. So this stems from the photon emission. These characteristic flat electronic states are there. And in the case of cobalting, it's non-magnetic, while iron tin itself actually has the anti-ferromagnetic order for the iron atoms. So in the non-magnetic case, we have a much better first principles understanding of the wave function in the system. So here I want to show you the calculated real space real space 1-year function of the flat band states in cobalting, and you can think about this as a proxy for the real space eigenstates of the flat band here. So what you can see here is a set of rotated d orbitals on this hexagonal loop, very similar to the real space eigenwave function we've seen earlier. So right. And here we can still see that a very similar mechanism of destructive interference is still at play. If we look at the hopping of 1 and 2 states to the third sites, for instance, the hopping from 1 and 2 as a combination to 3 would be strictly forbidden. And this, in the d orbital case, would come from these two 1 and 2 would have a different eigenvalue than 3 in the mirror symmetry, where the mirror plane is drawn here. So therefore, this is still a very good real space eigenwave function of the flat band. Right. So the point I wanted to make here is that although the model we started with was very simple, where we only considered isotropic hopping, but even with incorporating the realistic details of, for instance, the orbital degrees of freedom of the d electrons of cobalt, right, we still have the same frustrated hopping at play, and we still have the flat band physics still relevant. Even the starting point was a very simple. So not only we're able to see these flat electronic states from photon emission. So here I want to show you a result of the tunneling spectroscopy through one of the flat band hosting materials, iron tin. And in this particular case, we were tunneling between a semiconducting substrate to the metallic thin films. So the dIdV as a function of voltage, you can use this as a proxy for the density of states as a function of energy. Right. So we can see that there is indeed a peak of the density of states that's around the same energy where you see the flat band for the emission. And since this system is antiferromagnetic with the critical temperature around room temperature, as we warm up the system, we do see a smearing of the flat band itself, which and the location of this peak is also moving a little bit. So this is suggesting that perhaps as the antiferromagnetic order itself is weakened, the flat band, the location of the flat band itself is also moved a little bit, and there seems to be a very strong correlation between the antiferromagnetic order itself and the flat band itself. Okay, so the reason I wanted to show you here is to convince you that we're able to see these flat electronic states from multiple experimental probes. So up to now, we've sort of established the presence of this flat band somewhere in our electronic structure, but I haven't showed you what kind of consequences they can induce. So more recently, we were able to finally try to bring the Fermi level into the flat band, and this is one of the this is the material where we've managed to achieve this. So the material has the composition nickel through indium, and it still has this kagome levels of nickel that are AB stacked upon right upon each other. And you can also see this stacking sequence from the transmission electron microscopy cross section of these crystals. Right. So before we go to the experiments, already from first principle calculations, you can see that one of the most prominent features in the electronic structure is the flat electronic states across the in-plane two-dimensional brilliant zone that's located here. And this is a magnified view of the landscape of the flat band itself. In the plane, where you can see that these electronic states are indeed partially occupied, at least from the DFT perspective. Okay, so what we were first quite excited to see this flat electronic states in DFT, and we went to the lab and tried to measure the transport property of these materials, this material. And this is what we find. We're for the electrical resistivity as a function of temperature, right? We're able to see this characteristic trace. We're below about 100 Kelvin. You see approximately a temperature linear resistivity. Right. So as a reminder, if we have a conventional metallic system, which often obeys the conventional Fermi liquid behavior, the resistivity should evolve as a function of temperature with T square in the here. And this comes from the picture that all the excitation of this Fermi liquid are these well-defined particles around the Fermi surface, and the T square basically comes from the phase space for scattering for the low energy quasi-particle states. So the observation that we have a strong deviation from this Fermi liquid behavior in our system when the flat band is put near the Fermi level is indicating that very likely, right, these quasi-particles are no longer super well defined as in the Fermi liquid case. So this T-linear behavior is often called non-Fermi liquid or strange metal, depending on who you talk to. And this is a sketch of the strange metallic phase I've taken from the Quantum magazine, who always have very nice sketches. And so here you can see the brown parts are electrodes that's connecting to the material itself. So in this part, the electrons are in the conventional Fermi liquid states, where you can see very well-defined electrons or the quasi-particles. But within the material itself, the system is pretty much in a chaos, right? And there's a lot of fluctuations in the system, which invalidates the well-defined quasi-particles, and as a result, I will be able to see this T-linear resistivity behavior. So we don't have a 100% understanding of what is the origin of observed non-Fermi liquid strange metal behavior in our system, and one of the hypotheses we have is that perhaps the flat band electronic states in our system are forming local moments, which is very nicely illustrated in this News and View article about our paper here. So this localized states would behave as local moments as they are their kinetic energy are quenched. And there will be a competition between the localized moments themselves, as well as the localized moments with the conduction of electrons through the condor interaction, and perhaps this is the driving force of the strange metallic behavior we're seeing in our flat band system. So this is indeed a quite unexpected discovery we've made. We've encountered by being able to bring the flat band features to the formula. Okay, so with this, I want to summarize this part of the talk. Hopefully I have showed you that the kagome lattice containing metals, which we now call this class of material kagome metals, would be a really nice platform to search for flat bands. And by being able to bring the flat bands to the Fermi level, we're able to observe a non-Fermi liquid states in one of the members. Right. So aside from tackling specific questions about the nature of the non-Fermi liquid or strange metal behavior in the system, I'm also pretty excited to see a broader application of using the lattice to design flat bands, and also using the flat bands as the platform to see to study the physics of talk about new physics concepts. And one of the concepts is the quantum geometry of the band states, and which is related to how the states would evolve on this characteristic walk sphere within the flat band. Okay. So I think I've promised at the very beginning that we're gonna try to show you a few snapshots of what we are working on now in the lab. And so the next few slides will be pretty, will be a little bit scattered and quite open-ended, but if you find one of the topics interesting, I'd be happy to discuss in more detail afterwards. Okay, so in the first part, we're trying to use the frustration of lattice hopping to get the flat bands and try to get some unconventional electronic states from the flat bands. Right. So this project I'm trying to show you here is an idea that's also similar, but we are trying to harvest the frustration in the magnetic degrees of freedom of the system to really give rise to unconventional physical property responses, and this should be something tangible and potentially can be something useful. Okay, so in this particular system, we are able to grow single crystals, which are very which look like these prisms, and the cross section of these crystals actually corresponds to these distorted kagome lattices. Right, so here, thanks to magnetic frustration, a very exotic magnetic order is realized, where you can see that if we follow through across this hexagonal loop, you can see that the spin are sort of winding around the loop, and we can define as a toroidal moment for this spin configuration, which is sort of the momentum of the magnetic bonds. So there is, for this particular magnetic states, its time reversal pair, as shown here, where you can see here that this spins would wind the other way if you go around the loop here, and this would have an opposite toroidal moment in this state. So a peculiar a feature of both of these states is that they would both break the mirror symmetry, with the mirror plane being the plane you're seeing here on the screen. And at a very simple level, this would induce a difference in the for the transport property of the system, with the current flow into the board and the current flowing out of the board. And this is called the non-reciprocal transport. And in principle, the non-reciprocity of the transport response would also be opposite for the two different magnetic domains. So we've shown recently that we are able to use a moderate in-plane magnetic field to actually polarize the system into one of the two domains. And we are, you can see here from this length of the sample as a function of magnetic field, where this hysteresis near the zero field is actually showing that the system is in one of the domains. So we are still in the process of trying to assess how much this symmetry allowed non-reciprocal transport would be, and if we can really capture this, I think it would be a really cool physical response that's a result from magnetic frustration. Okay, so one of the other directions, I think Dave probably very briefly mentioned at the very beginning, that our lab is focusing on, is to try to develop different types of strain tools to tune the materials, and hopefully combine this with the material synthesis, we'll be able to access a broad range of phase space. So on the left are two examples of the piezoelectric-based uniaxial strain cells. And this is a biaxial cell, which is driven by mechanical deformation that we're developing right now in the lab. So both of them, this should give us different independent modes of deformations of different materials, and can hopefully bring us to new regions of the phase space. And the part I'm showing you on the right is perhaps more for the experimentalists in the audience. In our lab, we have vertical magnetic fields up to 14 Tesla, which is a very strong magnetic field. And we try to set up our strain cells such that the direction of the magnetic field can be rotated within the planes, three different planes that we're showing here, with respect to the direction you're deforming the material. So we are not able to achieve this in a continuous manner, but at least we are able to do this in a discrete way and access quite a bit of combination of the relative orientation of strain and magnetic fields. So one of the example of what we wanted to use strings to study, right? So this is some of our recent results using the string as a thermodynamic probe to frustrate the string systems. So in this particular experiment, we are studying the alpha ruthenium trichloride, which is the prime candidate of the material realization for our colleague Alexis bond frustrated spin model. So in our experiment, we apply a small AC string to the material and measure the temperature change that's induced by the string. And this, in principle, should give us information about the entropy in the system. So what we've identified is that near the region of the phase diagram of ruthenium trichloride, where the quantum spin liquid phase is proposed, we do see a large accumulation of entropy near this region. And one of the really cool experiments we can imagine doing, which may or may not be exceeding the ability of the strain we can apply reasonably in our lab, is that by applying strain to break the symmetry between Jx, Jy, and Jz, right? We might be able to tune our system in the different regions of Alex's phase diagram, where the different regions all have different types of unconventional low energy excitations. Okay, so with this, I want to thank my colleagues and collaborators at MIT for the first part of the talk, and also members of my current group, as well as the support for our current research. And I think we're at time, and I'd like to stop and take questions from the audience.
Okay, maybe I'll start with a question. So, can I ask about the holmium silver germanium?
Great.
Yeah. So,
Oh, yeah.
So for a toroidal order parameter, I thought you had to there's only linear coupling to a combination of magnetic and electric fields.
It's a cross of magnetic field and electric. So
how do you polarize with just a magnetic field?
I think there are actually other so there are other aspects of the magnetic structure that's helping this. So I believe these magnetic states are also piezomagnetic, but that's not it does not necessarily come with the toroidal moment.
I see. Okay,
So I think the nice thing about this material is that actually you have both properties, so that you can use the magnetic field to actually polarize the domains. I see. And then we'll be able to perhaps see the responses from this particular pattern of space.
Okay, thanks. Other questions, Jason?
Can I ask about ruthenium chloride?
Yes.
Very interesting data. What field orientation is it, and have you thought about probing different field orientation?
Yeah, that's a great question. So this is the magnetic field is applied in the AD plane, and in particular, I believe this is along the A-axis. It's perpendicular to the bonds. And we did apply the magnetic field along the axis, actually, and we see a much weaker divergence of the signal there. So I think that there's some. We haven't fully understood this, but my understanding is that that's also related to the Pitaev interactions.
Maybe a follow-up that
Yes.
some parts are blue, some parts are red, and I guess those are opposite sign in response.
That's correct. Well, let me get a little bit into the detail of the measurement itself. So you can think about this measurement measuring the strain derivative of entropy. So whenever you sort of have a peak, when you are at a field-induced phase transition, the entropy of the system will be at a local maximum, right? For instance, and if you take the derivative over some parameter, the maximum would give us 0, because we're taking the derivative for entropy. So you actually see a very characteristic dispersion curve if we take the field cut through this. So it's consistent with the fact that the probe itself is sensitive to the entropy of the system.
What type of phases in the spectrum? Presumably we have some magnetic order.
Correct. Yeah. So zero field. So this is an antiferromagnetic order. That's kind of I didn't show you here, but it's kind of a ferromagnetic along the zigzag chains, and then it's antiferromagnetic across the bonds. And the intermediate field phase, I believe it's a different stacking along the c-axis than the zero field zigzag order, but it's in some sense still a zigzag order. And I think there are proposals that once this is suppressed fully by the magnetic field, you would be dominated by the Majorana fermions predicted from the Kitaev model. And eventually, and this is also the region where quantized thermal Hall effect is claimed. And it's still controversial whether there is a finite field range for the quantum spin limit phase or not.
And what are J energy scales?
So I do need to check, but I believe it's a few tens of kelvins.
Sounds about right.
Few tens of kelvins.
So the field to polarize would be much larger, so I'm still very far.
That is frustrating. Oh, you mean fully polarized this field? That's a good question. We actually don't know the magnetic. So here is a paramagnetic phase, but I think I actually don't know how far away it's from being fluid.
Other questions for Linda? Yeah.
So here's a maybe off the wall technical question about your strain cells.
Mhm.
So you mentioned for the mechanical ones, how much force is involved?
I'm
I'm just wondering if in situ mechanical tunability be possible.
so I don't have the number on top of my head. One of my students.
Yeah, the reason I ask is that the bellows actuators we use for the diamond cells can put sort of 1,000 pounds of force while the system is cooled. So I wonder whether that might be an interesting tool to try to engineer in.
Might be. I think I know for the there are similar designs for photo emission experiments, and I think they do have the in situ tightening of the screws in some ways. That's probably
Because for the
good
diamond
dirt.
cell literature, as it were, there's a bunch of low temperature actuators that sort of 1-ton scale tunability.
Okay, maybe we should discuss that in the lab.
Yeah.
Any other questions for Linda? Okay, if not, let's give Linda a round of applause.